Right, recording is rolling for Wednesday, November 3rd. I've got a lab lined up for you guys today. You just saw me do the demo version of this before I started the recording, so we're a few minutes into class. Right, but we got these collision carts. Oh, whoops, let me zoom out so you guys can see. Right, you guys saw these carts. Now, there's magnets in these that have the same pole spacing, so if you have them collide like this, they go boing, that collide up elastically, like you guys just told me. And I have opposite pole magnets taped on the other side, so that it go this way, go click, and they'll like stick together. Click. That would be inelastic. You can also change the masses of these carts by just taking these lab weights and popping them on there like this. Okay, so that's the basic mechanics of this lab. I have this lab table for you guys. Now, there's only so many papers, so this page, I put a few of these out on the lab table. So you guys are going to have to share one per team. So you guys can write a few names on a lab paper. That'd be right. But this lab paper has two sides on it. And the tables look pretty similar, but there's a little difference. You can sort of see at a glance. You guys see like two bold columns here versus only one bold column on the side. You do like a side-by-side, right? So there's some small difference here. I wonder what that is. Well, we'll start with the side here. So zoom in. Now, since this is a collision lab, you guys are interested in something about momentum. Is momentum conserved? Might be a good question. I'm not going to have you guys do an AP style write-up for this one. I just want you guys to get your hands on these cards and collide them and record some numbers and see how this plays out. I'll have you guys do an AP style write-up for another lab coming up pretty soon. But my intention to put this together was that this is actually all one giant table, just in two halves. So there's this is labeled pre-collision, and this is post-collision. Okay? So you have one cart kind of like slam into the other, and I've got 5 trials on it for you guys. So this entire top row is the first trial. So this is like trial number 1, right, before the collision, after the collision, right, and then 2, 3, 4, 5. Okay, so you guys can get like 5 trials. Maybe change out the masses, something like that. Let me explain this sort of from the back. It's sort of backwards. Okay. So if you guys are interested in momentum, is momentum conserved? Let's hone in on what is this dark column at the end of this table. Looks like this right here. Okay. Well, it says momentum, and I give you momentum units, but it's grams centimeter per second. Maybe easier to measure that way at this lab. Hey, that's kind of like kilogram meter per second, right? You have this gram centimeter per second. Okay. So some kind of momentum unit. Now, how are you going to calculate what that momentum is? It has something to do with mass times velocity. Oh, well, I guess you would need a mass and a velocity. So make back all the way up to the start of this table. Okay, so now we can make sense of maybe what numbers would you need so you can eventually get to momentum so you can figure out something about momentum. Okay. So what's the mass of this part in grams? Now, I measured this ahead of time, which might help you out because I do have a digital scale back there, but this is too heavy for that. There's also a classic triple beam balance, which I do encourage you guys to get your hands on and try out, but if you can't access that, then the mass of an empty cart all by itself is pretty much exactly 500 grams. Okay. But this isn't quite that because I've taped on the magnet, so plus the magnet, plus the tape, plus this paper towel cushion. I'll say the mass of all the fun stuff, magnet, blah, blah, blah. That adds up to pretty close to 50 grams. So again, if you can't access the triple beam balance, if you want to say just the cart with the magnet tape on it, okay, it's about 550 grams. If you use that number, then this will work out. So mass of one cart, let's call it 550 grams. Let's say I just have 2 empty carts, and 2 empty carts can like slam against each other. So just 2 empty carts, they're going to collide like that. All right. So 550 and 550. So those are the 2 masses. And then, okay, so remember where this is going. To get momentum, we need mass times velocity. So, if only I knew the speeds of these things, right? The velocity. How are we going to get that? Oh, maybe some kind of distance per time, right? So have this thing rolling along that low friction track. Let's say I have it roll 50 centimeters and somebody brought a stopwatch and they're timing this thing and it comes out to 1.25 seconds to roll those 50 centimeters. Did you guys figure out velocity from that? Just it gives you guys the equation right here. Of course, since you guys are AP, you guys know in the back of your mind, you should be able to come up with this all from scratch. Yeah, I just really ideally hand you a blank piece of paper, you could figure out this whole thing, but no, we only got limited time here. Okay. So let's say 40 centimeters per second. Okay, 40 centimeters per second. Okay. Then, hey, what's the deal with this? Why did I zero out this column? Oh, okay. I'm having you guys start the other cart from rest so that it has zero momentum itself, right? Because mass times zero velocity would just be zero. Okay. So if you look at the poster I gave you guys for perfectly inelastic collision, that's the side of the paper that we're looking at right here. These two carts are going to collide and stick. Okay. Actually, it's even simpler version of this, because if V naught for object B is just zero, it just starts from rest. So it looks like all the momentum in the system is actually just coming from the one moving cart. You guys get that? That's how it's working. Right. How about post-collision? What's going on post-collision? Okay. Oh, that's what this happen table is for, like post-collision. Okay. So, oh, look at some of the masses, mass A plus mass B. So if it was 550 grams, together that totals to 1,100 grams. It's like one giant mass. Moving how fast? Ooh, okay. Well, here we need another distance and another time. So let's say you track out another 50 centimeters, and well, you guys just saw the demo. So after they collided, they did collectively move slower than the one was moving by itself. So let's say it takes, I don't know, like 2.5 seconds for that to happen. 2.5 seconds, right, to roll those 50 centimeters after these are stuck together. Okay. Now, notice if you're paying attention to the mechanics of how this work out, all these numbers all happen in a very small interval of time. What you might want to do is have one teammate timing this leading up to the collision. So, how far does the one cart roll, and how much time, so that you can get the speed as it's heading into the collision. Okay. And then another student saying those two stuck together, how far do they roll and how much time, so you can figure out the velocity after collision. But this all happens like bang bang. Or what you guys might be able to do, since you guys are pretty good with technology, is I'm sure there's some way where you can do some stopwatch function where you can like hit a button so that it stops this one and immediately starts this one. You just get it 2 times. Yeah. Okay. Yeah. So Ryan knows how to do. Okay. I'm sure you guys know that. I don't, but I'm sure you guys do. Right. So what's this velocity? Let's see. It went 50 centimeters in 2.5 seconds. That would be 20 centimeters per second. Right. Okay. Oh. So what's the momentum? Well, I got 1,100 grams at 20 centimeters per second. I forgot to calculate the other one. Here. Okay. So, okay, I'll just sort of in order. Right, go back a little bit. Pretend I didn't do that. Right, so before, remember, it was just the plain 550 grams moving at 40 centimeters per second. Okay, that comes out to 22,000 grams centimeter per second. Right. Now, I know it's a big number in the thousands. You guys get numbers in the thousands. But if you went with kilograms instead of grams, that's 3 decimal places. And if you went with meters instead of centimeters, that's another 2 decimal places. So couldn't you call this like 0.22 kilogram meter per second? Right. If you wanted numbers that are comparable to, say, the notes from the last couple of days. Okay. All right. So how about after the collision? Now I've got these two collectively 1,100 grams, moving at 20 centimeters per second. So, hey, look at that, 22,000 grams centimeter per second. Hey, that's the same momentum, isn't it? Right. Of course, I'm just making these numbers up and trying to give you guys an ideal situation. Okay. But this is the time I was putting this table together. I thought it'd be a good idea to have momentum before, momentum after. So just whatever this number is, just copy paste it down here. So 22,000 grams centimeter per second. Okay. And then copy paste this number, 22,000 grams centimeter per second. Ideally, those should be the same, and then if they are, then that verifies conservation of momentum. Okay. Now, realistically, if there's a little bit of friction in the system, which there is, what do you think the second number actually would be? A little bit more, or a little bit less? Probably a little bit less. If you get something like 18,000, then I would, compared to 22,000, I would say, ooh, that's plenty close enough. That'd still be really good. There's, okay, you guys good so far? Okay. So I've got a few more things I want to tell you guys though. Okay. One thing is, pick one row and compare kinetic energy pre-collision to kinetic energy post-collision. Okay. So not all of them, but just pick one row and do it. So I'll do it as an example for this right here. So I got 1/2 the mass of one cart times the pre-collision velocity squared. That's going to look like 1/2 times 550 grams times 40 centimeters per second being squared. Okay. So 1/2 by 550 by 40 squared. That's looking like 440,000 is the number, but that'd be gram centimeter squared per second squared. Okay. Now you could convert that to joules just by rolling the decimal back a lot of places, but okay. I mean, we're working with these answers. Okay. Okay. How about afterwards? I got 1/2. I got the sum of the masses, right? The two parts put together, right, times the post-collision velocity squared. Right? And I tried to pick a numbers that are you could intuitively work with, right? I mean, if you've got double the mass, but half the velocity, double mass, half the velocity, okay, that means the momentum's gonna be the same, just mass times velocity. But for kinetic energy, hey, if I have double the mass but half the velocity, don't forget that velocity is being squared. So it's like that factor counts twice, right? So is this kinetic energy gonna be the same, more than, or less than 440,000? Less, specifically by a factor of what?
Maybe.
Let's see, if the mass is double what it was before,
Yeah.
but velocity is half, and that half's being squared, guys, what's times 2 times a half times a half? Wait, times 2 times a half,
It's just 1/2.
yeah, and then times a half. Here, let's try it. What is 1/2 times 1100 grams times only 20 centimeters per second being squared? 1/2 times 1100 times 20 squared. It is 220,000. That is half of the kinetic energy. Gram centimeter squared per second squared. Okay, so it looks like during this inelastic collision, half of the original mechanical energy, like kinetic energy, was converted into other forms, maybe like deformation, heat, sound, all of that. Okay, you guys get that? All right. The other side of this page is set up for a different kind of collision, that elastic collision, where these two carts go like boing, like bounce off each other like that, like perfectly elastically, or ideally perfectly elastically. Let's see. So, well, it's a very similar thought process. Here's the difference. The difference is that post-collision, you got two carts each doing their own individual thing. So you have to calculate their individual velocities. So you're going to need 3 different times going on, right? The pre-collision velocity, start the other car at rest, just to simplify it a bit. But then post-collision, you'll have a distance and a time for each individual cart. So can you guys handle that? Okay. So this one's quite a bit trickier. But then if you add these two momentum values together, right, then copy paste that number right down here. This is just the sum of those two momentums. Ideally, these should be the same. And if you compare the kinetic energy before and after, then what should the kinetic energy be? Should be the same if it's perfectly elastic. Right? And you guys are going to see how close that actually is with a little bit of friction and all that stuff. Right? Okay. You guys good so far? Okay. Last thing I want to mention is that there's not enough time in class to do like all these, 5 rows on one side, 5 on the other. So aim for at least 3. Try to do like 3 and 3. And yeah, I know we got limited time. Right? So you guys can put several names on a page. Just turn this in by the end of class, and I will walk around and help you guys out.